I'm Carlos. I've been here since the beginning. I helped Kelly organize the first one and organize the second conference in 2018. I'm a philosopher of astrobiology, philosopher of science by training. And so today, I'm going to focus on the C part of SOCIA, right, the conceptual stuff. And this work is done in collaboration with a friend of mine named Rory Smead at Northeastern University, who wanted to be here today but had some family issues. He came up to me and said, I really want to be involved in this astrobiology stuff. How do I do it? I'm like, I don't know, let's talk. He says, well, I can do game theory. I'm like, perfect. All right, I'm gonna talk about a project I've been working on since grad school, universal biology, and show how game theory might fit into it, and then talk about some future directions. This talk is in this fun stage where I know it better than, or too good to keep into 15 minutes, but not good enough to make sure that it sticks to 15 minutes, so I'll work as well as I can. In astrobiology, a lot of the things that happen that scientists focus on and work on tend to be, honestly, it's the work that was done in the late 90s or the mid 90s in the Bay Area, but maybe a little bit less cynically, it happens to be where our instruments, our tools, our experiments, our evidence points us to. And so there's this is just a quick illustration. You can imagine people disagreeing about all of the details, but the point is that there's a lot of stuff that you might consider to be interesting that we're not really at the stage in science to worry about or to talk about. And really that's everything between metabolic signatures and exoplanets and technosignatures, right? All of the medium-sized that would be of interest to us. Which leaves it to science fiction. Not bad, just a thing to point out. And so I spent a lot of my graduate program worrying about this question of what life must be like. And so it's an area called universal biology. And there's a lot of assumptions built in that a bunch of you will jump out at the first one. Maybe Luis will challenge the first one, right? Maybe others will certainly leave by the time we get to number 3 that there is any way for us to know. But I want you to just set aside your skepticism for a hot second and imagine what it would be like to walk down this path, to see the kinds of areas that it opens up and the kinds of things that we can start discussing if we start focusing on a universal approach to biology. A thing that I've argued for all of those points in print, and I can go into detail about any of them, any of the assumptions, but today we're just going to assume you're following me. And there's a lot of people that have attempted to universalize biology. They tend to come from their own disciplinary backgrounds and try to attach their own disciplinary agendas and say biology is just a subset of their discipline, actually, which is a thing that we're going to do today. It's not a thing that I even disagree with. It's a lens by which to see the thing that we're talking about. So we're going to focus on evolution here. But I think a lot of people, when they think about evolutionary theory, they think that it ended with Darwin, right? They think that in 1859, Charles Darwin comes up with evolution by means of natural selection, and then we're done. Cool. In fact, the theory has been adopted and expanded and adjusted for a century and a half. And I often think about all of the nuances that go into what practicing biologists think about as evolutionary theory, and then the reductive version of it, which I think is what we learn in middle school and high school, tends to be very, very oversimplified. To wit, we know that smaller populations might drift more. That is, they change in stochastic, arbitrary, what's the word for stochastic? Random ways. And we know that there is a lateral transfer with microbes. not as much with macros. With macros, there's more sex, which is good, I guess, for us. We know that there's regimes where there's competition and ones without. We know that there's regimes where there's leaky resources and ones without, et cetera, et cetera, et cetera. And depending on the population you study, you're used to making these adjustments. You're used to focusing on the part of the evolutionary tool chest that you're working on, and we move forward. But some of those tools, I think, are more universal than others. And that's the stuff that I want to focus on now. But first, I'm going to talk about game theory, which is a branch of mathematics, a branch of economics, that really came into the fore in the past century. Traditionally, we now call it like a traditional game theory or economics, and it's the study of rational agents, how rational agents make decisions, how they strategically behave. And every one of those terms, rational agents act, ends up being circularly defined. It's problems that behavioral economists have pointed out in the 70s. We're not going to get into it, but they're really cool. But it really is the kind of thing, like, are you the kind of person that would behave this way, or am I the kind of person that you would think that would behave in this way? So that's like super duper, the smart game theory. There's also dumb game theory. You might call it evolutionary game theory. And this is the study of guessing and checking, basically. Over long enough periods of time, they tend to approximate each other, and in certain ways, they approximate each other. And there's a lot of different kinds, there's a lot of different games. You can get lots of different results depending on the setup. When we're talking about, for example, Michael's talk yesterday, we were talking about parks on Mars. And I was talking, like in my question, I asked about incentives, and that's coming from a game theory discussion. Like in game theory, we understand a lot of how this stuff works out, and so you don't blame the players, you blame the game. Yeah, that sounds. Forget I said any of that. All right, so the assumptions for evolutionary game theory are pretty simple. All you need is a thing to talk about and things that it prefers. That's it. Things that are better for it or worse for it. It doesn't even have to have preferences that are internal in any sort of representational way. And once you get that, these types could be strategies or against kinds. There's got to be these interactions, these things that are better for it or worse, and eventually you'll get change. Anything else you add on top of that is an interpretation layer, and that interpretation layer may be really important. It might constrain the kinds of change that are possible. It might open up new areas of interaction. It might make transitioning between certain game regimes to others a lot easier. But the math is really straightforward. And the math is this big equation. It's called the replicator equation, which, as a philosopher of biology, I hate the term and the concept of replicators. I actually don't think you need the concept of replicators to make sense of this equation. I'm not going to make sense of it because that's what my co-author does. But essentially, you separate the individual contribution from the environment, and with this, you can get the outcomes are predictive of broad trends in a lot of different areas. Things as diverse as evolutionary biology, social interaction with cultural evolution, machine learning, reinforcement learning, AI. We haven't mentioned AI yet. I know. Consider yourself happy. That's the last thing I'll say about AI. But the exact same equation can be used to describe frequency-dependent change. Frequency-dependent change, again, is any change that involves how other types, like my type, are going to be doing when they interact with me. So what ends up happening here is something Brian Skirms is called the Darwinian veil of ignorance. And this is where when you really, really start paying attention to the math behind interactions, you stop caring about individuals. You end up seeing strategies, and you end up seeing interactions, and it sort of makes sense why individuals fall the way that they do. You start like making sense of politics with game theory, like, oh, you know, reverse card to go. scientists think that they can do a version of this. We saw this with Richard Dawkins' selfish gene theory. We see this with thermodynamics. We see this with a lot of areas. Okay, now let me try to connect the two. And this is where I had to get some slides for time. Okay, hopefully it still makes sense. There's this phenomenon in most games and game theory called the Nash equilibrium, named after John Nash, a mathematician and economist from the 20th century, who developed an understanding of how games can get caught in these local cul-de-sacs, right? Like everybody knows that the best outcome in a prisoner's dilemma is for us all to cooperate. We can't really trust that you're not going to rat me out, you know? And so because that sneaks in, eventually everybody ends up in a worse position. Now, not all Nash equilibria are bad, some Nash equilibria are good, but these are like these little local cul-de-sacs where you can imagine better outcomes in other ways, you just can't get there because they're too far away. Or the amount of change you'd have to do would be too difficult. So as an example, outside of biology, we talked about sports, right? There's incentive for every player to cheat, so we put in referees. And referees change the kind of interaction, which means that you're changing the kind of game. You get a different Nash equilibrium. And so Nash equilibrium, a situation where no agents improve by changing their behavior. You assume you can't change society, so you might as well change yourself, and there's nothing better that you can do. And these behave as a kind of attractor in space. An attractor in game theoretical space. Now, I've presented some of this work to a lot of different audiences, and some of them come from chemical backgrounds or physics backgrounds or any number of other backgrounds. And the things that they will say to me is, yeah, this way of thinking is not the right way of thinking. We ought to be thinking about biology in my way. Cool. There's lots of ways of thinking about this. There's lots of interesting abstractions that we can make. The thermodynamic schools of universal biology lead to interesting conclusions. I just want to say that this leads to another set of interesting interactions, which hopefully I'll have time to get to. Okay. So, I think a lot of the people that have problems with universal approaches in general, abstraction approaches in general, tend to be the kind of people that focus on the strictly speaking false version of this. But strictly speaking false and approximately true are the same thing depending on your research question, right? So they really are. And sometimes the discussion is just like, oh, I don't like your research question. And I say, okay, cool. All right. If you walk far enough in it, there's interesting outcomes. Please, trust me. But hopefully I have time to get to some of these. Okay. All right. So how is this interesting outside of just giving us another theoretical branch for when biologists go out into nature and they find a dynamic? They don't have to say, oh, there must be something unique about hawks and doves. They say instead, no, this must be an instantiation of some general abstract form. That's just to piss off Lucas. Sorry, that. So one thing is that you can imagine situations where you'll see you'll find concentrations of muck on Europa or Titan or something, and you'll see dynamics, you'll see some sort of signal populations that can coexist or not, or cycle. And from those, you might be able to infer entire ecological behaviors, entire interaction type behaviors. So if you never see any interaction, that's kind of a no pure Nash equilibrium case, like rock, paper, scissors, right? If you always see one dominate, that's another type of game. And the game theory will give you a lens by which to see that. All right, so last slide. What I hope I've said, and I hope I didn't cut out any of the things that would have made you believe in me, is that there is a gap in astrobiological research, and that it actually can be explored in a fruitful, theoretically rigorous way, maybe not an empirical way. That it's worthwhile. game theory is a pretty good way of approaching that. But I think it's very, very fruitful, and I think it's something that I wish there were more of it in the